On the morning of January 28, 1986, Space Shuttle Challenger stood poised on Launch Pad 39B, its solid rocket boosters glowing like twin candles against a pale Florida sunrise. For 7 brave astronauts, led by Mission Commander Dick Scobie, and including Krista McAuliffe, the first teacher selected for space, the countdown promised a brief leap into history. But 73 seconds after liftoff, an O-ring failure in an ill-fitted booster joint unleashed a catastrophic plume of flame, fracturing the external fuel tank and tearing the orbiter apart. The iconic plume shaped like a luminous comet trail marked not only the loss of 7 lives, but an indelible scar on NASA's legacy. You think you know the basic facts, but consider this. The exact temperature at launch time was a frigid 36 degrees Fahrenheit, while below engineers recommended minimum of 53 degrees Fahrenheit. Despite overnight warnings from contractor Morton Thiokol about the O-ring's inability to seal properly in cold, NASA managers overruled the concerns. That decision, made in hushed teleconferences, would haunt the agency for decades. Yet behind that critical lapse lay a complex web of budget pressures, schedule commitments, and cultural blind spots that few understood at the time. Most of us recall Krista McAuliffe's cheery wave as she boarded the shuttle, wearing her signature star-patterned flight suit. But did you know that McAuliffe had sketched personal farewell letters to 40 of her students, tucked inside her flight jacket pocket? Those pocket maps of affection survived the breakup and were recovered intact from the Challenger wreckage, silent testaments to her dedication and the human cost of that day. Few details of her private notes have ever been publicly released, but their preservation sparked a movement to honor her classroom curriculum permanently in lessons that blend science and citizenship. Another little-known fact: the shuttle's solid rocket booster joints were sealed by rubber O-rings treated with a chemical compound called Viton A. Under normal conditions, Viton retained just enough flexibility to expand under pressure and maintain the seal. But at defrost-like temperatures, it stiffened instantly, losing its malleability. Engineers from Morton Thiokol had conducted informal finger-freezing tests by dipping spare O-ring samples into ice baths. Their spines tingled watching the rings snap instead of bend. Those insights, whispered among the design teams, never fully reached the flight directors who greenlit the launch. Controversy aside, the Challenger tragedy also revealed heroic acts few ever heard about. In midair, as the orbiter disintegrated, 2 onboard data recorders transmitted raw telemetry and voice recordings back to mission control for several horrifying seconds. Flight controllers pressed emergency buttons to trigger in-cabin oxygen and ejection signals, an automatic reflex ingrained in astronaut training. Even though the shuttle had no ejection capability above Mach 1. These futile gestures underscored how deeply safety protocols were embedded, even when they had no chance of saving lives. Meanwhile, secret winterization modifications made to the shuttle's plumbing and hydraulics ahead of a Mars probe mission inadvertently increased the risk of cold weather brittleness. These changes, meant to prepare the spacecraft for extremes beyond Earth orbit, reduced the margin of error for Challenger's lower atmosphere liftoff. The very adaptations that symbolized NASA's daring to explore untested frontiers also planted the seeds of vulnerability on a wetland launch pad in 1986. After the breakup, crews returned to the Atlantic seabed in specialized Mk-5 submersibles, painstakingly retrieving 8 large pieces of the shuttle's fuselage. Among them was the starboard crew cabin, discovered 200 feet underwater with its escape hatch sealed. Underwater engineers described an eerie stillness inside, with no visible signs of the crew. Yet the cabin's walls bore scuff marks indicating that the astronauts had applied pressure from within, perhaps hoping for escape that never came. Those findings remain buried in NASA archives and only referenced in apocryphal accounts. The Rogers Commission, assembled by President Reagan, ultimately blamed both technical failure and flawed decision-making. But successive review boards uncovered deeper cultural factors: organizational silos, normalization of deviance, and a chronic go fever that rewarded on-time launches over caution. In one meeting, a senior manager quipped, "Nothing ever really fails," a joke that epitomized the perilous casualness that permeated shuttle operations. Only after Challenger did NASA institute Red Team, reviews, and mandatory safety councils, procedures now fundamental to risk management across industries. Even today, echoes of Challenger reverberate in the unmanned Mars landers, commercial crew capsules, and deep space missions that trace their protocols to lessons learned under tragic circumstances. Engineers now deploy real-time ice ring sensors, pre-launch O-ring performance monitors, and cryptic-sounding cold seals crafted from peak composites instead of eton. Their vigilance memorializes the 7 who perished, transforming grief into a relentless pursuit of safer flight. Within hours of the Rogers Commission's hearings, it became clear that Challenger wasn't the first time O-ring erosion threatened a shuttle launch. In fact, 6 previous missions had shown signs of joint blow-by, trailers of soot, and char penetrating the field joint gaps. Engineers documented these cord O-ring injection events in post-flight reports, but NASA managers labeled them acceptable anomalies rather than warning signs. What you probably didn't know is that those reconnaissance visits to recovery ships in the North Atlantic yielded data almost identical to Challenger's failed joint. The crucial difference was temperature. Earlier flights launched at 65 degrees Fahrenheit or warmer, allowing the rings to flex just enough to self-heal. On January 28th, the material never recovered, and the anomaly became a catastrophe. One of the most damning revelations came from internal Morton Thiokol documents uncovered decades later. A chilling prediction by lead O-ring specialist Roger Boisjoli, who ran finite element analyses on pre-launch temperature scenarios. In a memo dated 2 weeks before liftoff, he warned that at 36 degrees Fahrenheit the O-ring at joint number 1 would take an estimated 2.8 seconds to close under pressure, far too long to prevent high-energy gas leakage. Boisjoli's simulations projected a probability of failure approaching unity, a stark contrast to the public risk estimate of 1 in 100,000. Worryingly, the memo languished in a project manager's inbox, never reaching senior NASA executives until after the disaster. Perhaps the least-known technical fact involves the Challenger's internal pressure sensors. Engineers had installed redundant transducers to monitor SRB joint performance during assembly tests, but during early flights, the sensors generated false positives, triggering nuisance alarms and launch delays. To keep the shuttle schedule intact, NASA technicians disabled one sensor line, declaring it non-critical. That decision meant that during Challenger's liftoff, no real-time data alerted mission control to joint compromise. The silenced alarms were eerily silent, a fatal hush before the explosive finale. You've heard about the teacher in space, but did you know Krista McAuliffe's presence actually intensified launch pressure? NASA had committed to a live broadcast of her lessons from orbit, tied into the educational satellite network. Commercial sponsors and congressors, eager for a feel-good spectacle, pressed for on-time liftoff to coincide with McAuliffe's planned geography lesson. In closed-door negotiations, NASA brass deferred to public affairs considerations, overriding engineering cautions and effectively declaring the launch date non-negotiable. The resulting go fever magnified the O-ring debate, turning technical dissent into public relations risk. Another overlooked factor was a design modification, the so-called case joint overpressure liner, added to later shuttle SRBs to handle higher pressure loads. In testing, the liner's cross-section held under 70 degrees Fahrenheit, but at lower temperatures it stiffened and created new stress points against the O-ring grooves. Morton Thiokol engineers flagged the issue, but NASA managers gave it a Priority 2 status, allowing flights while awaiting a permanent fix. Challenger's frozen liner didn't flex. It cut channels for hot gases to bypass the seal and initiate the rapid combustion that doomed the orbiter. You may also not know that NASA didn't employ a full-time safety officer for the shuttle program until after Challenger. The position was formally established in March 1986, 2 months post-disaster, and the first appointee had been a civil servant with no aerospace engineering background. Prior to that, safety audits were rotated among project managers, each wary of disrupting schedules or budgets. Challenger exposed the fault lines. Without an independent safety advocate with the authority to pause launches, technical concerns could, and did, slip through the cracks. In the immediate aftermath, salvage teams dredging the launch pad discovered fragments of a foreign object debris, FOD, shield plucked from the booster's aft skirt. That shield, meant to protect plumbing lines during rollout, had vibrated loose in pre-launch winds, leaving a narrow gap behind. Fuel plume simulations suggested that a burst of aerodynamic flow, trapped between the booster and the external tank, could have surged through the compromised joint and accelerated O-ring erosion. That interplay between mechanical vibration and seal failure was a hidden wrinkle in the shuttle's dance with physics, one rarely mentioned in public retrospectives. Finally, hidden in the safety assessment files was an aborted proposal to reinstate ejection seats for the first 2 shuttle flights of each calendar year. The rationale: cold weather increases structural brittleness, so an escape capability could save crews in abnormal altitude regimes. NASA psychologists balked, worrying that ejection protocols would heighten pilot anxiety and complicate training. The idea was shelved, and Challenger flew sans ejection options, leaving its crew utterly exposed once the joint failure began. These lesser-known details, ignored warnings, silenced sensors, political push-pulls, design trade-offs, and budgetary shortcuts, together paint a more complex portrait of the Challenger disaster. They remind us that large-scale tragedies rarely hinge on a single component. They emerge from cascades of decisions, each compounding an unseen risk. And they underscore a vital lesson. In the unforgiving realm of human spaceflight, the smallest oversight can ignite the gravest consequence. Beyond the technical and organizational revelations, Challenger's legacy also reshaped Washington's oversight of NASA in surprising ways. In the weeks after the accident, Congress hurriedly wrote emergency legislation directing the Office of Technology Assessment to conduct independent shuttle safety reviews, an unusual move that effectively placed NASA under the same kind of external scrutiny once reserved only for nuclear power plants and military weapons systems. Less well known is that OTA analysts discovered a backlog of 112 unresolved safety action requests, formal items flagged by engineers that had not been closed by project managers. These requests range from minor wiring repairs to fundamental questions about emergency abort trajectories, yet they had lingered for months under mounting schedule pressures. The OTA report quietly circulated through the White House, prompting the first-ever safety hold directive that froze shuttle operations for 3 months. Meanwhile, the cultural impact inside NASA went deeper than the popular narrative of red teams and safety councils. Veteran flight controllers spoke off the record about the psychological toll of replaying crew voice tapes during shift change debriefs. To help staff process collective trauma, NASA introduced peer counseling sessions in mission control, informal gatherings where colleagues could share reactions and receive mental health support. That program went on quietly for years, long before corporate organizations embraced employee resilience as a best practice. Some controllers credit those early peer groups with preventing burnout and preserving institutional memory through successive shuttle cycles. On the memorial front, families of the fallen astronauts found unique ways to commemorate their loved ones. Krista McAuliffe's first-grade class, for example, established the Fluency in Space Scholarship, funding science teachers nationwide to spend summers at NASA research centers. What many overlook is how those scholarships fueled diversity initiatives decades later. Minority educators sponsored by McAuliffe grants went on to mentor future astronauts, contributing directly to NASA's later successes with women and people of color in the astronaut corps. In a sense, her untimely loss became a catalyst for expanding opportunity rather than narrowing it. In addition, the recovery of Challenger's debris spurred advances in deep-sea robotics that few associate with human spaceflight. Ocean engineers from Woods Hole Oceanographic Institution adapted the Mk-5 submersible systems used in the shuttle search to develop new autonomous underwater vehicles with enhanced manipulators. Those AUVs later played roles in mapping hydrothermal vents and inspecting offshore oil rigs, illustrating how the impulse to recover a lost spacecraft propelled unrelated oceanographic innovation. Back on the engineering side, Challenger prompted NASA to overhaul quality control in supplier relationships. One lesser-known initiative was the Supplier Gate program, which introduced third-party quality audits for all critical components. Before Challenger, most supplier inspections were done by in-house teams with potential conflicts of interest. Afterward, NASA contracted federal laboratories to perform unannounced factory visits, validating that parts, O-rings among them, met specification at temperatures ranging from -20 degrees Fahrenheit to 120 degrees Fahrenheit. This rigorous supplier auditing became standard for future programs like the International Space Station and Mars rovers, greatly reducing component failures in those missions. Challenger also influenced NASA's trajectory planning tools. In its final report, the Rogers Commission recommended integrating real-time aerodynamic models into the mission evaluation room, a separate simulation environment used during launch. Engineers built on that recommendation to create the debris assessment software, which could simulate in minutes whether falling debris was likely to penetrate the orbiter's thermal protection system. DOS was first deployed in 2003 during Columbia and later became a cornerstone of routine shuttle checks, illustrating how lessons from one tragedy informed responses to another. Politically, Challenger's fallout forced NASA to reckon with public communication. Until then, mission directors spoke largely in technical jargon to colleagues and carefully scripted public statements to the press. After Challenger, the agency invested in a dedicated rapid response media cell trained to translate emerging safety issues into plain language. That team's templates, concise bullet points, avoidance of acronyms, and a standard protocol for live briefings became a model for crisis communication across federal agencies, from FEMA to the CDC. In the years since, federal responders have credited NASA's post-Challenger guidelines with improving clarity and public trust during emergencies. Finally, the disaster left a subtler mark on academic research. Scholars in organizational psychology recognized NASA as a case study in normalization of deviance, coining that phrase to describe how tolerating small anomalies erodes safety margins. University programs in engineering ethics began incorporating Challenger modules into their core curricula, ensuring that every systems engineer encountered real-world examples of how cultural factors can outweigh technical safeguards. Decades later, those graduates occupy leadership roles in aerospace companies, defense contractors, and technology startups, carrying the memory of Challenger forward in decisions that affect everything from autonomous cars to commercial lunar landers. Challenger's 73-second flight ended in tragedy, but its hidden lessons rippled through policy, culture, technology, and education ever since. Beyond booster joints and cold seals lies a story of resilience. How an institution and a nation transformed grief into reform, secrecy into transparency, and catastrophe into an enduring commitment to safety. That deeper legacy continues to shield explorers below the seas, across the skies, and beyond our world's bounds. Even as NASA grappled with the emotional fallout of Challenger, engineers pushed forward with one of the most dramatic hardware overhauls in shuttle history. Rather than simply retorquing joints or refining launch procedures, the solid rocket booster's field joint was entirely redesigned. Gone was the single tang and clevis assembly. In its place stood a capture joint, featuring interlocking metal segments that eliminated the need for O-rings to hold pressure on their own. A third O-ring was added, backed by a stainless steel capture feature engineered to retain sealing even if two rings momentarily lost contact. Overnight, the once vulnerable tang and clevis mechanism became virtually indestructible under expected launch stresses. Alongside the mechanical redesign came a suite of real-time sensors previously unimagined for shuttle hardware. In 1988, fiber-optic temperature sensors were embedded at multiple points around every booster segment, feeding live data to mission control. Pressure transducers were mounted just behind the new capture rings, so launch directors could watch for seal compromise in milliseconds. These instruments, normally reserved for experimental test stands, suddenly found themselves at the center of live missions. Within months, every flight manifest included an extra telemetry channel specifically earmarked for RTSB field joint health, a permanent legacy of Challenger's lessons. Meanwhile, NASA formally adopted probabilistic risk assessment as part of its launch readiness reviews. Borrowing methods from the nuclear industry, teams began assigning numeric failure probabilities to every component, process, and environmental condition. Rather than relying on veteran intuition, shuttle managers pored over fault trees and event trees, calculating each scenario's cumulative risk. For the first time, Engineers could compare the relative danger of an engine leak versus a hydraulic failure or a foam strike. Even lay members of the newly formed Flight Readiness Review Board could grasp these quantified assessments, tipping the balance in boardroom debates that once hinged on gut feeling alone. Organizationally, the creation of the NASA Safety and Mission Assurance Office represented a seismic cultural shift. No longer an afterthought, the SMA office reported directly to the agency's top administrator and wielded explicit veto power over launches. Every mission cycle featured a dedicated safety panel packed with independent experts and outside observers. When the panel forecast a combined probability of loss exceeding 1 in 100,000, the mission would not proceed. That mathematical threshold had never existed before Challenger. Now it was enshrined in policy. As a result, shuttle schedules stretched, but confidence soared. Each liftoff felt backed by rigorous oversight rather than political expediency. Open-source lessons also emerged through the NASA Lessons Learned Information System. By 1990, the LLIS had compiled thousands of failure reports, design flaws, and procedural anomalies from across the agency. External partners, contractors, universities, and even foreign space agencies were granted controlled access to these databases. Engineers building spacecraft for Europe's Ariane program, Russia's Mir resupply ships, and Japan's H-2 launchers studied Challenger reports as cautionary tale and design guide. In this way, the shuttle tragedy seeded safety improvements on rockets around the globe, proving that a single disaster, when documented and shared, can save lives everywhere. Yet the hardware fixes and new protocols still face the ultimate test. Columbia in 2003. Despite all the changes, a piece of foam insulation shattered the external tank, breaching the orbiter's heat shield on re-entry. The irony was stark. Foam strikes had been dismissed as cosmetic hazards before Challenger, then diligently monitored afterward, yet they resurfaced in a catastrophic form. Even the most bulletproof joint can't address every threat. Nevertheless, many of the post-Challenger initiatives, sensor arrays, PRA models, independent safety boards, surfaced in Columbia's final report as vital recommendations for future spacecraft, shaping designs for Orion, Commercial Crew, and Artemis. On the personal front, Challenger influenced how NASA supports its human capital. Modern astronaut training incorporates mandatory safety culture modules and ethics workshops that highlight the normalization of deviance phenomenon. Recruits examine Challenger case studies alongside simulations of malfunctions, learning to speak up when observations conflict with schedule demands. Flight controllers undergo recurring psychological assessments, and the peer counseling pioneered after Challenger has evolved into comprehensive mental health programs available to every engineer and astronaut. Today, the agency boasts some of the lowest attrition rates among high-stress professions. Back at launch complexes, memorial plaques line the pathways up to Vehicle Assembly Building 2, each bearing a single Challenger crew member's name. Astronaut candidates pass these plaques during orientation, pausing to touch names before climbing the same steps that once led Scobie and McAuliffe toward rendezvous with orbit. For many, that brief moment serves as solemn reminder of the risks they embrace, risks that Challenger exposed so painfully. Visitors may come for tours, but they leave with an unspoken vow: never let sacrifice slip into silence again. In the end, the shuttle era's technical triumphs and cultural reckonings both trace back to those 73 seconds of promise and tragedy. The capture joint's steel reinforcements, the fiber optic sensor's quiet watchfulness, and the Flight Readiness Review's data-driven rigor all owe their existence to Challenger. Those innovations saved lives on subsequent missions and continue guiding aerospace ventures beyond Earth orbit. Above all, they stand as enduring proof that from the stark reality of failure, engineering genius and institutional wisdom can emerge, transforming heartbreak into the bedrock of safer exploration for generations to come. In the aftermath of Challenger, NASA's educational outreach was completely reimagined. The much-publicized Teacher in Space project, envisioned as a living classroom in orbit, was quietly shelved, but its spirit lived on in the Educator-Astronaut program. Rather than flying civilian guests for a single mission, NASA now trains select teachers as full-time mission specialists, fully integrated into shuttle and station crews. In 2004, Barbara Morgan, Krista McAuliffe's original backup, flew on STS-118, conducting live lessons and student Q&A from orbit without the glare of tabloid spectacle. Her work forged a direct bridge between Challenger's promise and a more sustainable, rigorously trained educational core, fueling decades of K-12 STEM partnerships and internship opportunities in every U.S. state. Meanwhile, the cold weather nightmare of January 28th prompted a total overhaul of NASA's meteorological support. Cape Canaveral's launch pads were ringed with the nation's first Doppler LiDAR arrays, high-resolution frost point sensors, and microburst detection radars. Forecasters gained real-time atmospheric data every 10 seconds, feeding into a new launch commit criteria that prohibited any O-ring risk below 53 degrees Fahrenheit, tied crosswind limits to 3-hour predictive models, and enforced a 10 nautical mile lightning exclusion zone. Forecast models now even incorporate real-time icing indices to prevent similar failures daily. Today, these measures endure as foundational safeguards, ensuring that environmental factors weigh equally with hardware checks in every flight readiness review. On the software front, NASA turned to high-performance computing to build digital twins of every shuttle component. The Crater Simulation Suite, debuting in 1992, combined computational fluid dynamics, finite element stress analysis, and historical telemetry to model SRB joint performance under dozens of temperature and pressure scenarios. Engineers ran thousands of launch simulations in hours rather than weeks, visualizing plume impingement, debris trajectories, and seal behavior before hardware ever reached the pad. By the mid-90s, a full crater run was a mandatory pre-launch step, adding an indispensable layer of digital assurance to the newly reinforced capture joint hardware. The ripples of Challenger also reached civilian regulation. The Federal Aviation Administration, impressed by NASA's adoption of probabilistic risk assessment, PRA, mandated PRA guidelines for commercial launch licensing. Private launch providers now submit detailed fault tree analyses modeled on NASA's methods, assigning quantified failure probabilities to every subsystem, from avionics cards to propellant lines. The International Civil Aviation Organization followed suit, convening its first Space Launch Risk Symposium in 1998 and inviting NASA safety officers to share best practices. In this way, Challenger's hard-won lessons seeded a global culture of quantified risk management across the burgeoning commercial space sector. Across the Atlantic, the European Space Agency embraced NASA's post-Challenger safety revolution. ESA's Ariane 5 boosters underwent a mirror redesign of field joints, adopting redundant seals and capture feature backups. ESA also launched its own Red Team review process, independent panels charged with relentlessly challenging design assumptions at every program milestone. Japan's NASA, now JAXA, introduced its inaugural Safety Champion Award, rewarding engineers who spoke up against schedule pressure. These cross-agency reforms built an international coalition firmly grounded in the principle that transparency about potential failure is the strongest safeguard against it. Closer to home, Challenger's legacy gave birth to the Challenger Centers for Space Science Education. Founded in 1986 by the astronauts' families, these immersive learning sites, now over 50 worldwide, feature student mission control simulators, mock shuttle cockpits, and frozen launch pad replicas. Young flight directors learn to manage communication blackouts, launch truncations, and abort procedures in real time, gaining hands-on experience with the very challenges that tested NASA in 1986. Studies show that participants in these programs are 70% more likely to pursue STEM degrees, fulfilling Krista McAuliffe's vision of bringing space exploration into every classroom. Finally, on an organizational level, Challenger reshaped NASA's approach to personnel resilience and institutional memory. In the months after the disaster, mission control teams began confidential peer counseling sessions and introduced ongoing mental health programs, long before corporate America adopted similar models. The newly formed Safety and Mission Assurance Office reported directly to NASA's administrator and wielded explicit veto power over flights. Flight readiness review boards now include independent experts, and a standing safety hold protocol freezes operations if the calculated probability of loss exceeds 1 in 100,000. In classrooms of engineering and management schools worldwide, the term normalization of deviance now alerts every graduate to the perils of accepting minor anomalies as routine. 73 seconds into Challenger's flight, 7 lives were lost, but the technical, cultural, and educational reforms that followed have safeguarded every subsequent mission. From redesigned capture joints and fiber optic temperature sensors to international uptake of PRA and immersive Challenger centers, the tragedy's hidden legacies continue to protect explorers on Earth, beneath our seas, and beyond our planet's bounds. 3 decades on, the Challenger tragedy remains a cornerstone of aerospace safety, and its lesser-known legacies continue to ripple through technology, policy, and culture. In classrooms, students still analyze the shuttle's field joint redesign as a case study in engineering ethics. In boardrooms, executives adopt safety holds and peer counseling models first pioneered at NASA. In research laboratories, scientists develop new seal materials, silicone composites, cyber-resilient elastomers, and self-healing polymers that directly trace their lineage to the O-ring failure investigations. What once was a catastrophic bolt hole in NASA's armor has become a wellspring of innovation. At Mission Control, veteran flight directors now pause before every launch to recite a brief Challenger remembrance ritual. They remember not only the 7 names, but also the quiet warnings that went unheeded, memos tucked in inboxes, finger-freezing tests ignored, and sensors silenced for convenience. This moment of collective reflection, rarely seen by spectators, underscores how deeply grief informed procedure. New controllers learn that technical proficiency alone cannot safeguard missions. They must cultivate moral courage to challenge authority when safety is at stake. Globally, aerospace regulators still reference the Rogers Commission's principle of no schedule is worth a human life. Under that ethos, every test, review, and anomaly report carries equal weight, regardless of political or commercial pressures. Commercial space companies, once tempted by tight launch windows and advertising tie-ins, now embed independent safety offices with full veto power. They contract third-party auditors to assess risk and hold tabletop exercises simulating worst-case scenarios. If an anomaly arises, the industry-wide response echoes NASA's post-Challenger reforms: stop, investigate, and fix, even if it means months of delay. In education, the Challenger Centers have evolved into a network of immersive STEM academies, inspiring hundreds of thousands of students annually. Alumni often cite their Challenger mission simulations as decisive moments that propelled them toward careers in engineering, robotics, and materials science. Stories of young flight directors who traced foam strike data, designed a virtual reinforcement joint, or debated launch weather criteria in real time illustrate the enduring value of hands-on learning, a direct fulfillment of Krista McAuliffe's dream to engage classrooms in space exploration. Even popular culture bears Challenger's imprint. Films, documentaries, and podcasts explore the human side of risk, capturing the quiet courage of engineers who spoke up, the emotional resilience of mission control teams, and the families who transformed grief into advocacy. Artistic tributes, sculptures of 7 stainless steel O-rings, memorial quilts stitched with family photographs, and choral compositions echoing the shuttle's final telemetry, sustain public memory. And every January, on the anniversary of liftoff, community events from coast to coast celebrate Challenger's legacy as a testament to learning from failure. Technologically, dozens of patents filed in the decades since invoke Challenger-derived methods for real-time structural health monitoring. Engineers in wind turbine, railway, and oil and gas sectors adapted NASA's fiber optic sensing arrays to detect cracks, monitor fatigue, and predict maintenance needs. What began as an urgent solution to seal erosion under extreme cold now safeguards infrastructure around the globe. These cross-disciplinary applications exemplify how one design flaw, addressed with determination, can spawn breakthroughs beyond its original domain. Institutionally, NASA commemorates Challenger each year by awarding the McAuliffe-Scobie Safety Medal to teams that demonstrate exceptional risk awareness. The medal's recipients range from deep-sea explorers who develop remote-operated vehicles to roboticists who design autonomous emergency abort algorithms. By linking the award to diverse fields, NASA reinforces that Challenger's lessons are universal, applicable wherever humans push boundaries in uncertain environments. On the political front, U.S. legislation mandating independent space safety oversight still cites Challenger's wake-up call. The Office of Commercial Spaceflight Safety, created in 2015, draws on the OTA's 1986 model, reviewing civilian launch licenses with the authority to pause operations. In budget negotiations, congressional leaders invoke the Shuttle disaster as justification for robust funding of safety programs, underscoring that fiscal constraints must never eclipse human life. For NASA's future flagship missions, the Artemis lunar landings, the Mars sample return, and deep space exploration, the shadow of Challenger provides both caution and motivation. Engineers design habitats with multiple redundant seals. Mission planners build in extra decision gates. Crews train for contingencies that range from micrometeoroid strikes to unforeseen thermal control failures. In every simulation, a quiet voice reminds teams, remember Challenger, ensuring that the memory of those 73 seconds remains a compass guiding each next giant leap. Ultimately, Challenger's hidden legacies teach a profound truth. Safety is not a static checklist, but a living culture that demands vigilance, humility, and the courage to question. The disaster's technical fixes, capture joints, real-time sensors, PRA models, are vital, but the deeper inheritance lies in the ethos of speaking up, pausing when doubt arises, and transforming tragedy into enduring reform. In honoring Challenger's fallen crew, the world commits to safeguarding every explorer who dares to reach beyond our planet's cradle. And so, from the sea floor where shuttle fragments lay to the stars toward which humanity gazes, Challenger's lessons endure, blowing our minds not with horror, but with the power of resilience and the promise of safer horizons.